Hello everyone, my name is Nurul Alfia Istiqomah. In this presentation, I would like to introduce to you the application of generative adversarial networks, or in short we will call it GAN, in environmental engineering. This presentation consists of general and fundamental introduction of GAN, how does GAN work, how then we apply GAN, especially in this case for environmental engineering application, and last are the summary and conclusion of the application result. Let's start with the introduction part. Google Lens smart machine which can analyze the health status of the plane and image segmentation for self-driving car are the example of discriminative model. This model remarking the most striking success in deep learning because the model has the ability of mapping high-dimensional and rich sensory input into class label, or in the other word classification. The application of backpropagation and dropout algorithms resulting in well-behaved gradient. In the other side, how about the progress of generative model? First, to illustrate what is generative model, here is the illustration of discriminative model where the network are used to reduce, distill, and summarize information. If we flip this network, isn't that mean we can generating image or data? Yes, it is, and it's called backquery. Backquery means passing one hot target vector representing a digit backwards through an already trained network to generate some kind of ideal image of digit. However, the backquery results are the same given the same one hot vector and kind of average of the images in the training data with label. In the other side, people want to generate different images that look like an example of the training data. Some generative models will already exist. However, in 2014, a guy named Ian Goodfellow presented a different kind of network architecture to generate image which has spatial architecture. The structure is not bigger, deeper, wider, and not using fancier activation function or more advanced optimization. It is just structurally different. How is the structure different? Let's study how it is different step by illustration below. Here is the simple illustration of familiar classification model where the model tries to classify image of cat and not a cat. There will be also a classification model that tries to classify cat and fake cat. To train this kind of model, then we need real cat and fake cat training data. But how if we build another model to generate the fake cat image instead of providing it? This is then how the idea of generator coming. The generator then trained together with the classifier, or here we call it discriminator. In GAN, those generator and discriminator trained together follow the adversarial training, where the discriminator and generator set to compete against each other, trying to outdo the other, but getting better and better. Also, the clever part of adversaries training is we don't need to define detailed rules that describe a real image to be encoded into the loss function. Now, after introduce how the spatial structure of GAN, let's see how is GAN different from other generative model of label. In the max likelihood-based generative model, it is divided into explicit density and implicit density model. Explicit models assume some prior distribution about the data and use an explicit density function. However, the drawback of those explicit density functions are the generating samples process is very slow and resulting in low quality output. Generative stochastic networks, or GAN, is in the group of implicit model. However, this model is still utilizing Markov chain Monte Carlo methods, which don't perform well in high-dimensional space. In the other side, GAN defines a stochastic procedure that directly generates data, does not need Markov chain, and the clever property of GAN architecture is that the training of the generative model is framed as a supervised learning problem, even though generative model is actually unsupervised learning problem. What are the examples of the application of GAN? GAN mostly used for the generation of image. Further, with some improvement of general GAN model, the example here we can generate face aging image using conditional GAN. Another example, GAN was also used to translate photos into emoji. In the other side, GAN also have the potential to generating numerical data. For example, here there are two studies where they generated synthetic data for some kind of cases when there is limitation to obtain those kind of data in the real world. But what is synthetic data mentioned before? Synthetic data can be described as artificially generated data that is not collected from the real world events, which replicates the statistical components of the real dataset. And then in what case, for example, do we need synthetic data in machine learning? Those cases are, for example, first, when data utilization restricted due to the privacy matter, for example, to obtain health data and passenger data. Second, the case when we want to balance our data due to the presence of bias. Thus, some of the elements of the dataset need to be augmented. Also, the condition when the availability of the data is not sufficient due to the difficulty or cost-related matter to obtain the data. Thus, once again, we need data augmentation process. And then for application in the environmental engineering, most of the time we can find the study where a type of material used to degrade the pollution in wastewater. In this case, we can study the relationship between material properties with its ability to degrade pollutant using machine learning model. Or in the other word, this is kind of data-driven approach. In this data-driven approach, sometimes data augmentation is needed to be performed in case of the scarcity of the available experiment data. GAN, as the versatile new architecture for data generation, can be a promising approach for this condition. Now, let's see how does GAN work both fundamentally and practically. Here is show the architecture of GAN. We can see here the two main components of GAN. Those are the generator and the discriminator. Here we can see the generator get input from latent vector z, and then the generator is applied to z to obtain a sample x from the model. Both generator and discriminator have parameters that can be learned or updated by gradient descent. Generator is optimized after k times of optimizing discriminator to avoid overfitting. And after that, generator and discriminator are competing against each other and are playing a min-max game where the discriminator tries the probability of fake near to 0, while the generator tries to make the probability of fake near to 1. The global optimum is reached when the real data distribution is equal to generated data distribution. The image below in the slide here is illustrated how generator and discriminator learn over the training process. The three main steps of training GAN are illustrated as below. First, the discriminator is trained with the real dataset and labeled as 1. Second, the discriminator is trained with the generated data and labeled as 0. Third, generator is trained to get positive classification from the discriminator. And both of those generator and discriminator should be finally balanced. Now, let's moving on to the application practice. In this practice application, we will generate a synthetic data and analyze the output of the generated data. Here, the data used for the practice application is obtained for a journal publication with the title is prediction of carbon dioxide absorption via deep learning. The dataset here consists of 6 variables. 3 variables represent the characteristic of the materials, 2 variables represent the experimental condition, and 1 variable represents the ability of the material to absorb carbon dioxide gas. In the real field, it is not easy to collect this kind of dataset due to it need to be sorted out manually from the experimental result, where some consideration regarding the similar material and experimental condition need to be addressed. Therefore, data augmentation can be tried to extend the data size. And then in the right side here, we can see the logical flow of the modeling process. But let's just move on to the methodology of the modeling process. Here, the modeling application as shown on the slide. First, here the dataset will be transformed, and then we will build the discriminator with proposed architecture and parameter. After that, we will build the generator. Discriminator and generator will be trained with min-max optimization formulation where the generator wants to minimize the objective function and the discriminator wants to maximize the sum objective function. The evaluation of the loss will be presented in log-loss equation. After that, the result will be evaluated using some data visualization method. Now, let's see the application practice result. In this slide is shown the statistical description of the data set and the result of data transformation, where we want the data to be more symmetry or more look like Gaussian distribution. As we can see here, the before and after data transformation in the histogram plot form. In the process of building GAN, here we load the model from TensorFlow Keras library that have been imported at the start of the coding process. The generator and discriminator framework is built using sequential as shown there with the proposed architecture. And then the train function was built by following 3 training principles of GAN, as already mentioned also before in the methodology section. Now we define the training parameter including number of paths and learning rate, and also define the GAN model for the training. GAN used in this practice is named vanilla GAN, where the generator and the discriminator are simple multi-layer perceptrons. This is the simplest type of GAN, and it tries to optimize the mathematical equation using the stochastic gradient descent. And as we can see here in the training process, after 5,000 epochs, the training progress saw accuracy of 81.25%. After that, the higher learning rate was tried and resulting in higher accuracy as well. As we can see here, the accuracy became 90.62%. And these are the training progress plot of generator and discriminator, as well as the accuracy progress of the discriminator. From the training progress plot, we can see that discriminator loss decreased toward a small value and the generator loss increased to high value. One of the possible answers in this case could be that the discriminator is getting too good and the generator is getting stuck. Now, let's evaluate the generated data we obtained from the model. First, we observe feature by feature comparison. In cumulative sum and data distribution of the real and fake data, variable total volume seem has the close match. However, the variable temperature has the less match compared to other variables. After that, we observe the spread out of the real and generated data by box plot visualization. From the data spread perspective, real and generated data for each variable is in the similar range. However, here we can see again for the variable temperature, it has quite different data spread out. Next, we observe the statistical distribution of the data in general. The principal component analysis plot shows that the data pattern between the real and generated data are still different. It is also shown in the log and mean standard deviation of the real and generated data. In addition, the heat map also presented where the degree of difference are still distinct between the real and the generated data. And then in the next evaluation, we have all variables plotted against its normalized value to see the relationship of each variable, whether it's still similar or not with the real data. However, the result shows that the generated data are not yet able to reproduce data with similar connection or pattern as on the actual data, which this result in agreement with the principal component analysis plot result in the previous slide. Based on all the visualizations that have been shown, the result of synthetic data generative models from this study only able to follow the common trends in the real data but fail to capture any unique or specific present in the real data. And let's move to the summary and conclusion. So the novel part of GAN lies in the architecture and the adversarial nature of training two or more neural networks against each other. And for the summary, 3-step of GAN training loop consists of first train the discriminator with real data, and then train the discriminator with data from the generator, and plus is train the generator to get positive classification from the discriminator. GAN can be applied for the data augmentation purpose in order to improve the performance of machine learning application. And based on the practice in this study, the GAN was successfully trained. However, the generated data not yet properly matched with the real dataset. And then that's why furthermore, modification for the model and its hyperparameter need to be addressed to improve the model further. And in GAN image, the performance indicator can be seen directly from the image result. However, in GAN synthetic data, several types of visualization need to be addressed to comprehensively assess the generated data. And for the future study of this GAN synthetic data, application hyperparameter optimization algorithm, for example, the grid search or genetic algorithm, can be used to obtain best parameter for the training. Also, application of different type of GAN architecture to solve poor ability of original GAN in handling various type of variables, for example, categorical or mixed variables, can be applied to get a better generated data. Those are all of my presentation. Thank you for your attention. Hopefully you can get the meaningful information from this presentation.